Welcome back, students. In this video segment, we will take a look at two sections, sections 8.1 arc length and section 8.2 area of a surface of revolution. Both of the sections are relatively short and they're very closely related to one another, so I thought it would be a good idea to have them both in one video segment. So let's get started right away. In the first section, 8.1, we're interested actually in both of these sections, we're looking at two applications of the definite integral. In Calculus 1, you learned at least two applications of the definite integral. The first was area between two curves, and the second one involved volumes of solids of revolution, or solids that are born of cross sections. If you took me for Calculus 1, we didn't look at the concept of the volume by cross sections. We looked at volume of surface of revolutions. In any case, in these two sections, 8.1 and 8.2, we look at two more applications. The first is that of finding not the area or volume involved with a function, but the length of a curve. We're interested in the length of a function between 2 points, x equals a and x equals b. So here's our function y equals f of x. So let's say let y equal f of x. And we're interested in finding the length of the curve. So the idea is to find the length of the curve between x equals a and x equals b. So what we're going to use, or what we're going to do, is use a really common trick especially in physics. What we're going to do is we're going to imagine taking the curve from x equals a to x equals b and cutting it into an infinite number of little sub-arcs, little bits of the curve, and then we're going to sum up each of those little bits. So specifically, let's say we'll cut the curve, or we'll look at one little infinitely small bit of the curve. We'll call it ds, and that little bit of the curve represents just one infinitely small bit that we've chopped up the entire curve into. And I want to find a formula for that little bit of curve, that little arc length ds, and then we'll use integration to sum up all those little arc lengths. So let's give that little ds, that little arc length, some dimensions. Okay, so let's imagine that the little arc length ds is formed by observing a small change in x, infinitely small change in x, and another corresponding infinitely small change in y. Now the little figure that we see in there looks almost like a right triangle, but it's not quite a right triangle. The hypotenuse, if you will, quote unquote, is not actually linear. Remember, ds is not a line. However, if we choose ds small enough, then that little arc length will be approximately linear. Now we're assuming that ds is infinitely small, so the amount of error involved or introduced in assuming that ds is linear is also correspondingly infinitely small, that is 0. And this little trick in allowing us to look at infinitely small bits of quantities called differentials actually can be made rigorous, can be made precise in what's called differential geometry. There's a whole area in mathematics devoted to doing that. So we're going to assume that ds is so small that that little sort of triangular figure is actually triangular. Okay, and this works out really well ultimately. Okay, so let's take a look. Let's blow up that little tiny triangle figure so we can get a handle on a form for ds. So in the picture off to the right there, and a little below, that's that little arc length ds that's blown up so that we can look at it a little more critically. So that, remember that ds is so small, then the amount of error involved in assuming that it's linear is infinitely small. That is 0. Okay, so here are the dimensions that I had pictured. There's the horizontal dimension dx. There's the corresponding dy. The differentials d to indicate that we're looking at infinitely small quantities. And then we get a relationship between dx, dy, and ds by geometry, by the Pythagorean theorem. So let's write a relationship then between these three quantities. So dx squared plus dy squared equals ds squared. And I want to solve for ds. So ds equals the square root of dx squared plus dy squared. Okay, so our total length, the total length of the curve, so the total length, and we'll use L for length, is then just the sum as x ranges from a to b. And I'm using the integral sign, not the sigma notation for sum, because when we're adding infinitely small bits, that is differentials, the sum becomes integration. Okay, so we're adding up all the little ds's. Well, it looks like a really nice simple formula. All you have to do is integrate 1 with respect to s. However, you notice the limits go from x equals a to x equals b. So we need ds to be in terms of x. We need to integrate with respect to x. Okay, so let's take a look at what we get. Well, if I substitute the radical expression I have for ds, I get ds then equals the square root of dx squared plus dy squared. And that's no better than the original expression. In fact, it looks more complicated than just integrating 1 with respect to s. We've never seen an integral of this form. So what we're going to do is we're going to force this integral to look like something that we can deal with. So this is x goes from a to b, and I'm going to take that radical, the square root of dx squared plus dy squared, and I'm going to divide by the square root of dx squared and multiply by the square root of dx squared. You know, we're assuming that dx is an infinitely small change in x. In fact, we can assume that it's positive. So this is x goes from a to b, and combine to one radical, at least the stuff in the middle of this integral. We can write this as the square root of dx squared plus dy squared over dx squared. And we can write the square root of dx squared as simply dx. So this is dx. Now it's looking more like an integral that we can handle. In our integrals look like an integral sign, then an integrand, and then dx or dy or dt or whatever. So it's looking a little better. So we no longer have to write in the limits of integration x equals a. It's just a to b. Since we're integrating with respect to x, the dx indicates that the limits of integration are x limits. And I'm going to simplify the integrand. I'm going to separate into two fractions, dx squared over dx squared, which is 1, plus dy over dx, quantity squared, dx. That was pretty slick. We have all of these quantities, familiar quantities to us. Dy dx is just f prime of x. Okay, so you can think about this as in terms of a final formula is the one we have there, or we can write it as 1 plus y prime, or f prime of x squared dx. And there's one of two formulas we have for arc length. Okay, so let's take a look at a specific example. Let's find the length of a curve. Let's say find the length, for example, find the length of the curve y equals 1/2 x squared minus 1/4 times the natural log of x. Real strange looking function for x between 2 and 4. Okay, so let's do that. Well, look at our formula. According to our formula, we're going to need y prime. So let's find y prime. Y prime then is x minus 1 over 4x. Remember, the derivative of the natural logarithm of x is 1 over x. So let's find our length. So the total length then of our curve is the integral from 2 to 4. So we're integrating between 2 and 4, the square root of 1 plus y prime squared dx. Y prime squared dx. All right, so let's put in the quantity that we found for y prime. So this is the integral from 2 to 4 of 1 plus, and the derivative was x minus 1 over 4x squared with respect to x. Now this section, both of these sections, 8.1 and 8.2, are coming after a whole long list of sections where we have techniques of integration. The strange thing here is that a lot of the integrals that end up representing the quantities of length or surface area from our next section, they're actually integrals that don't fit the formulas and the methods that we've studied in previous sections in chapter 7. And this is one. This is one of those. What I'm going to show you with the evaluation of this integral is something that happens really often in sections 8.1 and 8.2, and it's just a trick. It's just a trick that will serve you very well. Okay, so let's expand that integrand. Let's expand the stuff underneath the square root sign. Okay. So we have 1, and I realize I put a minus in there. So underneath the square root sign, it's 1 plus. So we have 1 plus, and then I'm going to expand x minus 1 over 4x using just the square of a binomial formula. So off to the side, I'm going to be using a plus b quantity squared is a squared plus 2ab plus b squared, something we learned real early on in first semester algebra, years and years ago for you guys. Okay, so, or I guess we're using a minus b, so doesn't matter. So we'll see we have a plus or minus b. So if it was a minus b squared, it would be a squared minus 2ab plus b squared. So x minus 1 over 4x quantity squared is x squared minus 2 times x times 1 over 4x plus 1 over 16x squared, and then integrate that with respect to x. Well, it looks like this integrand is just getting really complicated. Let's work with it a little more. Let's do some more algebra on it. So I'm not gonna move things around underneath the integral sign. I'm gonna leave the 1 where it is, and that's part of the trick. So 1 plus x squared, and look at what happens with the middle term here on that expanded binomial. You have 2 times x times 1 over 4x. 2 times x times 1 over 4x. Well, the x cancels, and 2 divides into 4 twice. So really, it's like minus 1/2 plus 1 over 16 x squared. Okay, and just for emphasis here, I'm going to put in parentheses that result of that we got from squaring the x minus 1 over 4x quantity squared. Okay, now notice the last 3 terms, the stuff in the red parentheses underneath the integral sign. The middle term is subtracting 1/2 or minus 1/2. Now I'm going to combine that 1 that we have underneath the integral sign with that 1/2. I'm going to actually perform that subtraction. but I'm gonna not move that number or that result first. I'm gonna move it so that it replaces that minus 1/2. Now, if you didn't follow along, combine like terms. 1 take away 1/2 is 1/2. 1 over 16x squared. Okay. Now, compare, here's the trick. Compare what's in the red parentheses in the line just above with what's under the radical sign now. The only difference is the sign or the operation, minus and plus. Now back to the red parentheses. That minus 1/2 corresponded to the original x minus 1 over 4x quantity squared. So if I had plus 1/2, I put plus 1/2 in the place. I'm going to do that in green. If I put plus 1/2, now look underneath the integral sign with the parentheses. If I put a plus there, that means I'd have a plus above. And here's the trick. That means I'd have a plus in the original parentheses where before I expanded that binomial. So if you haven't caught on yet, that whole expression underneath the radical sign simplifies into x plus 1 over 4x quantity squared. And we have to recognize this in order to be able to integrate this. Like I said, this integral doesn't fit one of our models that we have in Chapter 7 or Calc 1. We just don't have that. But look, we're integrating now the square root of something squared. And all we have to do then is cancel the operations of squaring and square root. That's the trick. And again, it's going to happen in homework. It's going to happen in lecture, I believe, in 8.2, and also at least a few times in homework. And it'll happen again in Calculus 3 when we pick up with arc length in 3 dimensions and stuff. So, okay, so now it's a very simple integral. We simply evaluate the integral. The integral of the antiderivative of x is 1/2 x squared. Antiderivative of 1 over 4x, remember 1 over 4x now is just 1/4 times 1 over x, so its antiderivative then is 1/4 times the natural log of the absolute value of x taken between 2 and 4. So let's get a number out of this. So let's substitute the upper limit of integration. We're using the fundamental theorem here now. 4 squared is 16, half 16 is 8, so plus 1/4 log of 4. Minus, at the lower limit, x squared is 2 squared or 4, half of 4 is 2, and then plus 1/4 times the natural log of 2. Funny looking ln. Okay, let's do a little more with this. So we have combining like terms. We're here. We have 8 minus 2 is 6. We can factor out a quarter. Natural log of 4 minus natural log of 2. Feel free to pause the video if you're not sure about my arithmetic. So 6 plus 1/4 log of 4 over 2. Laws of logarithms, log of a minus log of b is log of a over b. And finally we get 6 plus 1/4 times the natural log of 2. And I'd like you to think about what the units of this would be. Remember, our quantities are physical quantities or geometric quantities. So in Calc 1 we looked at area and volume. Now we're looking at length. So what are the units of this answer? Okay, they're not square units. They're not cubic units. They are simply units. We're looking at units of length. So they're not square units or cubic units. They're just units. Okay. Now I mentioned before we did this example that we have our formula, which is one of two formulas for this section 8.1. The big thing here, the big thing is our formula, the integral of ds, the sum of, if you will, all the infinitely small ds's to get the entire arc length. okay, as x ranged from a to b. This was the simple version of our formula, and we found that ds, and in physics circles or in engineering circles, the ds is called the differential element of arc length. The differential element of arc length looks like 1 plus, I'm going to rewrite it, 1 plus dy over dx squared dx. Okay, and we did some geometric juggling to get that. The original ds was the square root of dx squared plus dy squared, and I got the usable differential element of arc length by dividing and multiplying by the square root of dx squared. Now, if I wanted to get a similar expression where I integrate with respect to y, then I would multiply and divide by the square root of dy squared instead of what I did about 10-15 minutes ago, and multiply divide by square root of dx squared. And the bottom line here is that our second formula then, if we combine to one radical, we get 1 plus dx over dy, the derivative of x with respect to y squared, dy. Or, oops, that doesn't represent dy, that represents ds. Sorry about that. So let me clean this up. So the bottom line is that we have two different differential elements of arc length. 1 plus y prime squared dx, and that allows us to find the total arc length by integrating with respect to x, or 1 plus x prime, that means dx over dy squared dy, and that allows us to integrate with respect to y. So when you're finding arc length, you have a choice to make. Your choice is am I going to integrate with respect to x or with respect to y? Very often the choice is made easy because the statement of the problem will involve y as a function of x or x as a function of y, and then you just choose the formula, the easier formula. So specifically in our last example, I stated the function, or I stated our original curve was y as a function of x. So integrating with respect to x would be really natural. So in our second example, which is coming up right now, I'd like to take a look at using the other differential element of arc length. So I want to find the length of, and we'll call the curve x equals 2/3 times y minus 1 to the 3/2 for y between 2 and 5. Now, since x is a function of y, integrating with respect to y seems to be a little natural here, seems to be natural. Okay, well, after I do this example, I'm going to show you that we don't have to, just because our formula or function is given x as a function of y, we don't have to integrate with respect to y. It truly is our choice. Sometimes it's very difficult to solve for the other variable in the original problem. But in this case, solving for y wouldn't be so bad. So I'm getting ahead of myself here. So let's find the arc length. Our arc length, if we're going to use the second formula, is going to require dx dy. So taking the derivative, using a chain rule here, bring the 3/2 down, exponent down, multiply by 2/3, cancels out. So we get y to the -1, decrease the power by 1 to the 1/2 times the derivative of the inside with respect to y, which is 1. And our total arc length then becomes the integral, as x ranges between 2 and 5, of the square root of 1 plus x prime squared dy, or the integral between 2 and 5 of the square root of 1 plus dx dy is of y minus 1/2 to the 1/2 power, and then we square that because that's part of the formula, dy. Well, the integral is real simple. This is the integral from 2 to 5. The square root of 1 plus square and square root cancel out. I get y minus 1. Integrate with respect to y. And we get a super simple integral to evaluate the square root of y. Okay. Or tubes. I think we can go, no, we'll just go ahead and write that as a power. Y to the 1/2, integrate with respect to y. Add 1 to the exponent, 1/2 plus 2/2 is 3/2, so 2/3 y to the 3/2, integrating between 2 and 5, and we get our solution. 5 to the 3/2 minus 2 to the 3/2, which is just fine. You could write 5 to the 3/2 as 5 radical 5 if you wanted to, and similarly for 2 to the 3/2. And our units of length, arc length, are units. Okay. Now suppose that I chose to integrate with respect to x instead, or suppose that, yeah, actually that'll work. Suppose that I choose to integrate with respect to x. So suppose I choose to integrate with respect to x. And that choice is ours. There are two formulas for arc length, and we get to choose either one. So in order to do that, I'm going to need to take my original x equals 2/3 times y minus 1 to the 3/2, and I'm going to need to solve that for x. Oh, sorry, solve that for y. So if I multiply both sides by 3/2, and I need to solve for y, so if I raise both sides to the 2/3 power, I get 3/2 x to the quantity to the 2/3 power equals y minus 1. Finally, that gives me y equals kind of a strange looking function, 3/2 x in parentheses to the 2/3 plus 1. Well, my formula, if I'm going to integrate with respect to x, is going to require y prime. Let's take the derivative. So 2/3 comes down. So I have 2/3, and it's not going to cancel with the 3/2 because the entire 3/2 is multiplied by x, and that's being raised to an exponent. 2/3 decrease the power by 1, negative 1/3, times the chain rule will give us times 3/2. And that allows us to cancel 2/3 and 3/2. So 2/3 and 3/2 cancel. So I'm looking at 3/2 x to the negative 1/3 power. Okay, and my arc length then is the integral, and it's not going to be between 2 and 5 because those are y limits. Our arc length will be, we'll get the limits in a minute, the integral of the square root of 1 plus y prime squared dx. Well, I suppose we should get our limits of integration now. Well, if y equals 2, then x equals 2/3 times 2 minus 1 to the 3/2, which is 2/3. So the lower limit of integration is now 2/3. Lower limits of integration have to be x limits since we're integrating with respect to x. And if y equals 5, then x, by our original formula, equals 2/3 times 5 minus 1 to the 3/2. Now it's getting a little complicated. 2/3, 5 take away 1 is 4. 4 to the 3/2 means the square root of 4, 2. 2 cubed, 8. 8 times 2/3 is 16/3. All of that just to get the upper limit of integration. Okay, and let's proceed with this. The integral is not looking as simple as the integral that results if we choose to integrate with respect to y. So we get 1 plus the derivative, y prime, is 3/2 in parentheses to the -1/3. So if you square that, you get 3/2 x to the -2/3. Ouch. Look at that integral. The integral is actually doable. It's doable. We could do this. But it would take a little bit of actually, it would take a lot of algebra to get this to a point where we could make a u substitution on it. I'm going to summarize that by saying, yuck. Now, why would I do this? Why would I take an example where integration with respect to y would be so much simpler than do this? The reason is we didn't know ahead of time the difficulty level of the integral that would result in finding arc length. The only reason we chose to integrate with respect to y was we were given our function as x is a function of y. So suppose we were given this in terms of y is a function of x. Suppose we were given this arc length as, or this curve rather, as this funny looking y equals 3/2 x quantity to the 2/3 plus 1. Well, if we didn't think about this in terms of finding the best possible formula, we would end up with having to integrate this yuck integral. So the bottom line is this: we don't always let the way the function is given to us decide what formula we're going to be using. We want to choose a formula that's going to minimize our work. You choose one formula, you'll have an integral. You choose a different formula, you may have an integral that takes a fraction of the time or 10 times the amount of time. So how are you supposed to know? Well, for most of the problems you're going to find in the homework, if you just use the formula that's sort of indicated by the statement of the problem. If you have y as a function of x, then choose the one that integrates with respect to x, and vice versa. If you have x as a function of y, choosing the formula that integrates with respect to y, that pattern of thinking will generally lead to an integral. It's not so bad, but use some sort of common sense. If you end up with an integral that's unrecognizable or difficult by choosing one formula, then maybe before evaluating that integral, you try switching formulas. You may get a simpler integral that results. And that's going to go for our next section, 8.2 as well. Okay. Well, that does in fact end section 8.1. Remember, we're doing 2 sections today, so in this video segment. So let's start section 8.2. In this second section for this video segment, we're going to take a look at section 8.2 again, and the idea is to take the curve whose length we were finding earlier and revolve that curve about either the x-axis or y-axis and generate not volume like we did in Calc 1, but surface area. I want to figure out the surface area that's generated by revolving a curve about either the x-axis or y-axis. So what I'm going to do is I'm going to spend most of the time talking about revolution about the x-axis. Then we'll develop a real simple formula and look at an example. Then I'll give you at the same time, I'll give you the formula for the surface area obtained by revolving or revolution about the y-axis. And then I'll turn you loose to do some homework problems. Okay, so let's take a look at our basic fundamental problem. We're starting out with our curve, y equals function of x. So let's say let y equal a function of x between 2 points, x equals a and x equals b. And the problem is to find the area of the surface generated by revolving the curve about the x-axis. Find the surface area. Find the surface area obtained by rotating or revolving the curve about the x-axis. And later on we'll look at the y-axis. Okay, so I use a symbol that we use real commonly in Calc 1 for revolution. I'll put a little circular arrow going around the x-axis to indicate we're going about the x-axis. And the idea is very much the same as the idea for arc length. We imagine dividing up the curve. Before spinning it about the x-axis, we divide up the curve into a whole bunch of, meaning an infinite number of, little arc lengths ds. And then we generate a formula for the surface area obtained by revolving just that little portion ds about the x-axis. Now imagine rotating the curve, the entire curve around the x-axis, and then separately the little ds about the x-axis. What we'll generate is something that looks like this. So in the next picture, which I also did off camera so that it would actually turn out semi-decent, is I drew a picture of the actual surface that's generated. It looks sort of like a flower pot or something on its side. And in Calc 1 we were interested in the volume of the flower pot. Now we want to figure out the surface area. We want to figure out the amount of paint, if you will, required to paint the outside of the flower pot. Okay. Now just take the little ds arc length and imagine it's just that being spun about the x-axis. What we would generate is a tiny little band of surface, little band of surface. We want to find the surface area of that one little band and then use integration by adding up the surface areas of all those typical little bands. Well, those little bands, remember, ds is so small, is so tiny, that we can assume that ds is essentially a little tiny arc length, a little arc length, a little tiny line segment. So that little band that results by rotating ds about the x-axis is really just a little tiny piece of a cone. Okay, remember we're assuming that ds is really, really small. So that little ds is just a tiny little portion of the surface area of a cone. So all I need to do is figure out what's the surface area of a little band, a little bit of a cone. So let's isolate ds. Let's isolate that little ds. There's that little ds isolated again. Okay, so the idea is to imagine that one little ds revolved about the x-axis to generate a tiny little band of a cone or a portion of a cone. Now here's the amazing thing. If we take that little ds and spin it about the x-axis, we generate that little portion of a cone. And the amazing thing is, if we were to flatten out, or rather take the little ds and make it horizontal and then spin it about the x-axis, we wouldn't be generating a little thin band of a cone. We'd be generating a little thin band of a circular cylinder, a right circular cylinder. Okay, so in the next picture below, I imagine that I leveled off. I made the little ds's, instead of being having a positive slope, having a little positive slope, I imagined leveling them off and spinning that little ds about the x-axis. The geometry says And if you ever want to see a proof of this, I can write one up for you. It's really kind of neat. It's kind of amazing, actually, that if you flatten out that little line segment, sort of centered about the midpoint of that segment, and then revolve it, you get a portion of a right circular cylinder of surface area, and the surface area stays the same. It doesn't change. So the surface area, let's say the surface area we get by revolving that little horizontal segment is nothing more than 2 pi times the radius times the height of that little right circular cylinder, which is ds. Okay, so I want to give this thing a radius. Well, the radius is in the y direction. The radius is in the y direction, so I'm going to call it y. So the surface area is 2 pi y ds. And that surface area turns out to be the same. And again, this is from geometry. This is not a calculus argument that goes on in making this true. That surface area turns out to be the same as the surface area of a portion of a cone, 2 pi y ds. If I keep the same y and I keep the same ds. And this turns out, again, to be the same from geometry. This is a geometric argument, and you're not responsible for it. If you're a math major, and there are a couple of math majors in our course, I believe, in every calculus course, you'll actually likely prove this if you take a course in differential geometry or in just geometry at the level higher than junior high or high school geometry. So this tells us that we get a final formula for our surface area. So I'm kind of going really kind of backwards up here. So back up to our formula for surface area. The surface area generated by revolving the surface y equals f of x about the x-axis. Now we're going about the x-axis, not the y-axis yet. Is the integral of 2 pi y ds as x ranges between a and b. Look at how simple that formula is. Well, we have the same problem we did in the arc length problem. What is that ds? Well, that's the bad news. The good news is we already have two formulas for ds. We already have two formulas for ds. So here's our bottom line. Surface area, leaving off the limits of integration from above, surface area about the x-axis is the integral of 2 pi y ds. Well, we have two formulas for ds that we looked at in section 8.1. If we choose to integrate with respect to x, then we use ds equals the square root of 1 plus y prime squared dx, or the alternative formula, ds equals the square root of 1 plus x prime squared dy. Our choice. We're still going about the x-axis, but we choose whether we're going to integrate with respect to x or with respect to y. So it's not the axis of revolution that determines if it's dx or dy that we're integrating with respect to. It's our choice. The y in the 2 pi y ds formula doesn't change either. It stays in the formula. There's a little bit more to talk about with that y in the formula in a minute. So let's take a look at one example. Let's take a look at an example. So our example is to find the surface area, find the area of the surface or surface area generated by rotating, let's say, the curve given by y squared equals 4x plus 4 for x between 0 and 8 about the x-axis. Okay. Now notice we're not given x is a function of y or y is a function of x. We have to solve for one of the variables. So we choose, it's our choice, what we want to do as the person doing the problem. We choose if we're going to integrate with respect to x or y. Let's do both. Let's assume, just so you see the difference, let's assume that we choose to first integrate with respect to x. That means I'm going to need y as a function of x. Well, it would kind of be a good idea if we knew what the curve looked like. So let's take a look. Let's take a look at the graph of the curve. You'll see why we kind of need a graph here. The curve y squared given by y squared equals 4x plus 1. 4x plus 4. Do you remember what that looks like? Well, you might have forgotten. It's been a little while since you had pre-calc. But this is almost a standard form of a parabola that opens to the right. If we factor out the 4, we actually get the standard form of a parabola that opens to the right. So let's take a look at just a really rough graph of this thing. Okay, so the function then, or it's not a function of x, but the graph is a parabola that opens to the right. It has a vertex at -1, 0, so I'm going to need a little negative axis, and opens to the right. Okay, well, we kind of need a portion of this curve. So let's say we're looking at y being positive. So in the statement of the problem, we kind of need. Actually, I was going to say we kind of need to know whether y is positive or negative, but we don't. In retrospect, it really doesn't matter. If you take the parabola that opens to the right and spin it about the x-axis, it doesn't matter if you take the upper half or lower half and spin it about the x-axis. We still get the same surface area. Okay, so we're safe there. We don't have to identify ahead of time whether y is positive or negative. To make things simpler on us, though, we're going to need to make a choice when we solve for y. If we solve for y by taking the square root of both sides, we're going to get y equals plus or minus the square root of 4 times x plus 1, or y equals 2 times the square root of x plus 1 if we choose to do the upper half or rotate the upper half only. Doesn't matter. I'm going to choose the upper half of the parabola, since rotating the lower half or both halves is still going to generate the same surface area about the x-axis. Remember, we're going about the x-axis. So in our formula, we're going to need y prime. So y prime equals, well, the original function now of x has 1/2 as the exponents. It's a square root. To take the derivative, the 1/2 comes down, multiplied by 2 cancels. We get x plus 1 to the 1/2 minus 1, which is -1/2, or in radical notation, 1 over the square root of x plus 1. So there's our derivative. So now our surface area. Our surface area, S, or if you want, SA for surface area, is, the basic formula is 2 pi y ds. Real simple formula to remember. Of course, the background is that we have to remember the ds, the differential element of arc length from 8.1, has two separate forms. Well, we're integrating with respect to x. So I'm choosing to integrate this with respect to x, means that my formula now becomes 2 pi y, the square root of 1 plus y prime squared dx. Okay, so that's a little better. And my limits of integration are, in the original problem I had x varying between 0 and 8. So x goes from 0 to 8. Okay. Now, we're going to have to do substitute a couple of things in this integral. First, the y prime that we just found, and then notice that we have 2 pi y. We have 2 pi y. I'm going to need to substitute the original function in there because I'm integrating with respect to x. If I chose, and you should listen very carefully here, this will come up again in about 10 minutes. If I chose to use the form of ds that integrates with respect to y, then I wouldn't do anything with that y. I would leave it there and then integrate with respect to y. But since I'm choosing to integrate this with respect to x, I must substitute our original function, y equals 2 times the square root of x plus 1, because I'm integrating with respect to x. Okay, so let's do that. My integral then becomes the integral, x goes from 0 to 8, 2 pi y, 2 times the square root of x plus 1 times the square root of 1 plus y prime. Remember, y prime is 1 over the square root of x plus 1. 1 over the square root of x plus 1. That's y prime, and then that's squared in the formula. Then integrate with respect to x. That integral looks terrible, but it's really not so bad. It's really not so bad. So this becomes the integral from 0 to 8, 4 pi times the square root of x plus 1, okay, times the square root of 1 plus 1 over x plus 1, all under the radical sign. dx still looks pretty nasty, but it's not so bad. Trust me. If you don't trust me. You'll find out in a few seconds it's not so bad. Now let's look under the integral sign. I'm going to write underneath the integral sign 1 as x plus 1 over x plus 1. Looks like I'm making things even more complicated, but it turns out pretty nice. 4 pi square root of x plus 1. Now here's where we get the good stuff happening. In the numerator we have x plus 2. We can split this into 2 radicals, fraction with 2 radicals. And here's the nice part. This integral now is simply 4 pi. Oops, I don't want green there. It's simply the integral, and I've still got green. Let's see here. 4 pi times the integral from 0 to 8 of the square root of x plus 2 with respect to x. A very easy integral. That's my way of saying I'm not going to do it on camera. If you need, you can let u equal x plus 2, and you can stop the video or come back and do it yourself if you want. Very simple integral. So after integration, we end up getting 8 pi over 3 times 10 to the 3 halves minus 2 to the 3 halves. And just like in surface, or rather arc length in the last section, we have units to associate here. So what are the units? Well, what are we finding? We're finding surface area, so our units are square units. Cubic unit. No, square units, sorry. Surface area, square units. Okay. Now this is the result of our choice to integrate with respect to x. I want you to see another integral, or the integral that results if we choose to do the same problem, still rotating about the x-axis. The problem's not changing, but I want to choose to integrate with respect to y. So now, suppose we choose to integrate with respect to y instead. Our choice. The formula, basic formula, does not change. The formula for surface area is the integral 2 pi y ds. But I'm going to choose now to integrate with respect to y. So 2 pi y ds is the square root of, from 8.1, it's the same differential element of arc length, 2 pi y, 1 this times the square root of 1 plus x prime squared dy. Okay, now notice again, look back again at what we had to do when we chose to integrate with respect to x. In the formula for surface area, we have 2 pi y. So if we choose to integrate with respect to x, we're going to have to substitute the original function as a function of x into the integral formula. Now, we have the same integral formula, but if we choose to integrate with respect to y, we need not, in fact, we cannot substitute anything for y. Y is already the interval, or the integral, I'm sorry, the variable of integration. So we leave it. Okay. Well, we have a little work to do. We have 2 pi y, and we're going to need the limits with respect to y, and we're also going to need the function with respect to y. So off to the side here, off to the right here, our original curve was y squared equals 4x plus 4. I'm going to need to solve for x so that I can find dx dy, or x prime. That's our original curve. So to solve for x, I'm going to subtract 4 from both sides. And then I'm going to divide by 4. So x equals 1/4 y squared minus 1. So our surface area then becomes the integral of 2 pi y times the square root of 1 plus dx dy, x prime. Look at the formula. X equals 1/4 y squared minus 1. So dx dy, the 2 comes down, so you get 1/2 y. That's dx dy, but that's squared. Integrate with respect to y. Now our limits of integration need to change. Our limits of integration before were x was 0 and x was 8. Well, if x is 0, then what's y going to be? Well, remember, y is equal to 2 times the square root of x plus 1. Remember, our y is equal to 2 times the square root of x plus 1. Watch your eyes. I'm scrolling a lot here. Sorry about that. So if x equals, sorry about that, I'm still getting used to my surface here. If x equals 0, then y equals 2 times the square root of 0 plus 1, or 2. So the lower limit of integration is now 2. If x is 8, x was 8 before, y equals 2 times the square root of 8 plus 1, x plus 1. 8 plus 1 is 9, the square root of 9 is 3, 3 times 2 is 6. Okay, and that's the integral that we integrate. It looks very different from the integral that we, limits of integration are 2 to 6. It looks very different than the integral we looked at if we chose to integrate with respect to x. It's not a difficult integral. If you square out that 1/2 y squared under the integral sign, you're just looking at the integral from 2 to 6, 2 pi y times the square root of 1 plus 1/4 y squared. And it's a simple u substitution. All you do is you let u equal 1 plus 1/4 y squared, and things really just roll out real nicely. Again, another easy integral that I'm not going to integrate on camera. Okay, if you did the integral, you'd get the same result. The surface area doesn't change depending on the method that we apply to find it. All right. The big point here, though, is just like in 8.1, we choose whether we're integrating with respect to x or with respect to y, and it doesn't depend on the axis of rotation. So I want to summarize what we have so far, and I want to introduce you to the formula that we would use for surface area rotating about the x-axis. So surface area about x-axis. Surface area about the x-axis, the formula is the integral of 2 pi y ds, which means that it's 2 pi y times the square root of 1 plus y prime squared if we choose to integrate with respect to x, in which case we're going to have to substitute our function in for y right next to the 2 pi y, or 2 pi y times the square root of 1 plus x prime squared with respect to y, and we make no substitution in a 2 pi y. We integrate that as part of the integral. Okay. So finally, if we want a formula for surface area about the y-axis, I think you can probably guess what the formula would look like. If we choose to integrate, or rather not integrate, if we choose to revolve the curve about the y-axis, what do you suppose changes in the formula for the surface area about the x-axis? It now becomes 2 pi x ds. It becomes 2 pi x ds. So the formulas, if you want to see them all written out, 2 pi x, and if you choose to integrate with respect to x, you substitute that that ds from section 8.1 as the square root of 1 plus y prime squared dx, and that x and the 2 pi x just stays there. It stays under the integral sign just like that, just like that. Now the formula, if you choose to integrate with respect to y, is still the integral 2 pi x square root of 1 plus y prime squared, not y prime squared, 1 plus x prime squared, got caught up in my own formulas here, x prime squared dy, and in this case you need to substitute, it's the worst looking T. Let me fix that. You need to substitute x as whatever the function of y is for the curve. Then you integrate with respect to y. Okay, so just to make sure, because this is a common place where students get caught up. It's not the axis of rotation that dictates whether we integrate with respect to x or with respect to y. It's us. We choose to integrate with respect to x or with respect to y based on a couple of things, based on and it's all part of our experience, based on if the original problem has y as a function of x or x as a function of y, or we choose to integrate with respect to x or with respect to y based on the difficulty of the integral that results. If you choose to integrate with respect to x and get an integral you can't handle, whether it's surface area about the x or y axis, switch to integration with respect to y, and perhaps we'll get an easier integral to evaluate. In any case, that ends our 2 sections for this video segment, sections 8.1 and 8.2. And I'm looking forward to talking with you all again soon.